All right, Chapter 7 cheat sheet. This test is going to have 6 questions on it, scattered throughout the 5 sections from this chapter. I'll be breaking this down in order, not only demonstrating what the questions are, how they're going to be asked, but I'm looking for also in scratch work. So here we go. So our first problem is referenced right here in section 1. In section 1, we dealt with angles inside of polygons. And the main formula that we learned in section 1 dealt with how to calculate out what the internal angle sum should be for any number of sided figure. This one happens to be a 4-sided figure. On your test tomorrow, I will tell you right now, it will have more than 4 sides. But in either case, we end up using the same formula to figure out what the internal angle sum should be. And the internal angle sum simply means that we're adding up the number of angles on the inside of the given figure. There happen to be 4 in this one. There will be more in tomorrow's test. So in section 1, we learned a formula in order to figure out the internal angle sum. I'll deal with that in a second. And the second part of this problem is going to be, now that I know what the internal angle sum equals, I'm going to add up or sum up together these angles to equal that number. So this will have 2 parts to it. First, I'm going to figure out what all 4 of these angles should add up to. And the second thing will be, I will actually add them up algebraically to equal that number. All right, so the formula that we learned here in section 1 was as follows. N minus 2 times 180 degrees. Now that N represents the number of sides of the figure. This one happens to have 4. Your test tomorrow will have a figure with more than 4 sides to it. So be prepared to plug in a different number for N. But in this case, I will be plugging in 4 for N. Okay, so as I go through this process, please keep in mind that your problem tomorrow will have more sides. So in this case, N happens to equal 4 because it's a 4-sided figure. And when I do 4 minus 2, here in this parentheses, 4 minus 2 is 2. That 2 times 180 degrees would tell me that the internal angle sum should equal 360. So again, this problem has 2 steps to it. Step number 1, figure out what your internal angle sum should equal. Yours will not equal 360 degrees tomorrow. I'll tell you that right now. Because it's a 4-sided figure, 360 degrees. Great. Part number 2, now that I know what the internal angle sum should equal, now I'm going to actually add up the angles on the inside of my polygon. There are 4 angles to add up here. And even though nothing's written here, this box implies that this is in fact a 90-degree angle. So be prepared to see something like that on tomorrow's test. So knowing that that box angle is 90 degrees, let me add those 4 angles up together. Box is 90 degrees. Let me just make my way around. So 90 plus the x plus 27 degrees plus 48 degrees plus x plus 73 degrees. There are my 4 angles. Their total altogether should be 360 degrees. Again, your figure tomorrow will have more angles and should have a different interior angle sum. So at this point, this is now a traditional algebraic equation. I have a bunch of stuff equaling to something, and my job here is now to solve for the variable using traditional methods, namely collect like terms and then move stuff away from the variable using inverse operations. So let's go through that right now. If I were to combine my 4 numbers right here, don't be a hero, use a calculator. 90 plus 27 plus 48 plus 73 gives me 238. So combining my like terms of numbers together, I get 238 degrees, right? Beyond that, I have these 2 variables, a positive x and a positive x. Adding those 2 together gives me positive 2x. And this is still going to equal 360 degrees here on the right-hand side. All right, so my job still is to solve for this variable. So now that I've collected like terms, my job will be now to move stuff away using inverse operations. The first thing I want to move is this positive 238. I would subtract that from both sides. And if I subtract 238 from 360, I get 122 degrees. And over here on the left, I still have 2x. So 2x equals 122. I move the 2 by division. 122 divided by 2 gives me 61. X equals 61 degrees. Done. You can see that once you get to the actual equation part, the process is probably something that you will be more than familiar with. Just collecting like terms and moving stuff away using inverse operations. So just have faith in that. But again, just to break down what problem number 1 will look like on your test, it basically breaks down into 2 pieces. First step, figure out what your internal angle sum will be. Again, it will not be 360 degrees on tomorrow's test. Be aware that you're going to be plugging in a different number of sides here for this formula. Once you know that amount, that's going to be on the right-hand side of the equation. And then you're going to add up all of those angles on the inside. This one happened to have 4 angles. Yours will have more tomorrow. You'll have that equation, collect like terms, use inverse operations to solve for the variable. Done. There's problem number 1. All right. Problems numbers 2 and 3 are going to be referenced here in section 2 and section 3. Sections 2 and 3 basically were flip sides of the same coin, right? And sorry, X and Y. You'll have multiple variables to solve for in these ones. All right, sections 2 and section 3 were basically flip sides of the same coin. We introduced the shape of a parallelogram. So of the polygons, a parallelogram is a 4-sided quadrilateral. What's unique about a parallelogram is that it is a 4-sided figure in which opposite sides are parallel to each other. And in section 2, we talked about a handful of theorems that were associated with parallelograms, basically baggage that comes along with that title. Namely, that opposite sides have to be congruent to each other. They'll have the same length. Opposite interior angles have to be congruent to each other. They'll have the same degree measurement. Consecutive angles on the inside will be supplementary. They'll add to make 180 degrees. And we learned that the diagonals of a parallelogram have to bisect one another. They need to chop each other in half. Section 3 was essentially the flip side of the coin. So in section 2, we started with the fact it's a parallelogram and all those theorems tagged along with it. In section 3, we started with the actual inverse of that, the converse of the theorem rather. Namely, I have a 4-sided figure with opposite sides that are congruent. Therefore, it must be a parallelogram. So essentially, they're flip sides of the same types of ideas. So what will you see? All right. Let me use an example first that is pulled from our notes, and then I'll talk about what will be different for what you will see on your actual Chapter 7 test. Gotta make sure I try and make this as much a parallelogram as possible. Okay. So in our notes for section 2 and section 3, you were given things like this, okay, where you were given some information, whether they be angles or lengths of sides, and you're asked to solve for variables. So in this case, in this figure, we're going to be asked to figure out what X and Y have to be to force this figure to become a parallelogram. So we're actually going to be referencing some of the theorems we learned in section 2. Here's what I mean. In order for this shape to be a parallelogram, opposite sides need to be congruent to each other. That means they need to match. So let me start with that one. Opposite sides. The opposite sides theorem that we learned in section 2 told us this. In order for this to be a parallelogram, opposite sides need to be congruent. And if opposite sides are congruent, that means that this 3y minus 1 side length needs to match or be the same length as this 20 length side. And so from an algebraic standpoint, I would simply set myself up with this equation. 3y minus 1 is congruent to or must equal or match the 20 opposite it. And at this point now I'm solving this the traditional way. I collect any like terms, and then I move stuff away from the variable using inverse operations. So for instance, I would move this 1 by adding it to both sides, and I would get 3y is equal to 21. Then I would divide by 3 to find out that y is in fact 7. Simple enough once I have the equation. Now to solve for the x for these angles, I'll be referencing a different theorem. So let me just reference that really quickly. In this case, I'm going to be using the opposite angles theorem. And what we learned in section 2 is that for opposite angles, in order for a shape to be a parallelogram, on the inside, these opposite angles, again, need to be congruent or match. So from an equation standpoint, that 2x degrees in the lower left-hand corner needs to match the 54 degrees in the upper right. And then again, using regular inverse operations at this point, I would divide both sides by 2 to find out that x is in fact 27 degrees. Simple enough in that point. All right, so again, what will essentially happen is you'll be given a diagram. You're referencing the theorems that we talked about up here in section 2 and section 3. Again, they're all listed out in those section notes. And then using those theorems, you're going to be able to create a very simple algebraic equation to then solve for the variable. All right, so let me take a little side step from that. And I want to actually show you what you're going to be getting on your test tomorrow, because there will be a slightly different strategy for one of them. Okay, so on your test tomorrow, you'll see something like this. You'll be given a parallelogram like that. All right, and I'm going to give you 3 of the angles. This guy, and this guy. So I'm not going to give you the 4th one. And then each of these ones that I give you will be some sort of algebraic phrase. All right. And so just like before, just like we did on this example above, you're going to be referencing some theorem that creates an algebraic equation. One of them will be just one of the ones that we referenced up here, namely opposite angles will force whatever algebraic phrase is here to be equal to whatever algebraic phrase is down here. You'll have an equation, you'll be able to solve for a variable. Simple enough. The tricky one will be this guy. Okay, there are actually a couple different ways you could attack it. I'll give you the simple way. All right. First off, the one that I will not be able to use is opposite angles. Okay, it would be tempting to just be like, all right, well, I'm going to set this algebraic phrase, whatever it is, equal to whatever's up here. Problem is I'm not given anything up here. And it would be tempting for a student to think like, oh, because nothing's written there, it's 0. And that's just simply not true. This is definitely more than 0 degrees, right? But whatever algebraic phrase is here, I can't use opposite angles because I'm not given the other angle to compare it to. But there is another theorem that I can reference in section 2, and that's consecutive angles. Consecutive angles. So consecutive angles told me that angles that are next to each other or in a row, okay, so for instance, these 2 angles are consecutive, or these 2 angles are consecutive, that these consecutive angles need to be what's called supplementary. All right, meaning, let me just give these quick labels really quickly. If I call this A, I'm not going to need it, but B, C, and D, all right, angle A and angle D need to be supplementary. Angle D and angle C need to be supplementary. So I could say, for instance, that the measurement of angle A, whatever algebraic phrase is here, plus the measurement of angle D, whatever algebraic phrase is here, has to equal 180 degrees. Because that is what we would call supplementary. I could also have done the same thing with D and C. It doesn't matter which one you do, because what ends up happening is that since these 2 guys are congruent or the same, I can actually interchange them right here. So whether you put in angle C or angle A, either way, I would add it with angle D to figure out it's 180. So whatever algebraic phrase is here, or here for that matter, but whatever algebraic phrase is here, if I add it to whatever algebraic phrase is here, it has to equal 180. And then I'd have another algebraic sentence. I just collect like terms, move stuff away from the variable using inverse operations, solve that method. But I just want to show you this is what you will actually see on tomorrow's test. All right, so that's problem number 2. Problem number 3 is going to be similar. I'll show you kind of a broken down version just so you can get the gist of what's going to be happening. All right, so that was problem number 2. Problem number 3, you're going to be asked the same sort of thing. You're going to be asked to solve for variables, and you're going to see something like this. I'll give you a parallelogram. Ugh, try that again. Wow, made a mess. All right, I'll give you a parallelogram like so. But now I'm going to give you diagonals. And just to use one that we referenced in our notes, all right, you might be given something like this. All right. And it'll be phrased exactly the same as problem number 2. Here is a 4-sided figure. We want this to be a parallelogram. And in order for it to be a parallelogram, certain properties or theorems need to be true. And in this case, since we're dealing with diagonals, what has to be true is that these diagonals will chop each other in half. Now, for the record, on your test tomorrow, this segment here will also be given a length, and this segment here will also be given some algebraic phrase length. And I just wanted to do it this way to keep it clean, and it's going to end up using the same strategy for these two pieces right here, just like it would for these two pieces right here. But in this case, we're going to be referencing the same theorem for both of them. Even though I didn't give you one here in this example for this, you can expect that in tomorrow's test. There will be 2 parts to this. But they'll both be referencing the same theorem, namely the diagonals theorem. What the diagonals theorem says in section 2 is that in order for it to be a parallelogram, these diagonals need to bisect one another. What does that mean? That means they chop each other in half. More specifically, since this longer diagonal here has to chop this guy in half, that means each half, this 2x version up top here, and this 10 minus 3x version down here, need to match, need to be congruent. In other words, I can simply set myself up with the following equation. 2x needs to match or be congruent to or be equal to that 10 minus 3x. Again, on your test tomorrow, you will also be given this segment length in an algebraic phrase, and same thing with this one, some algebraic phrase. It'll be the same thing. You'll set each one equal to each other just like this. I just want to keep it simple here. And now, just like before, I collect like terms, move stuff away from the variable. So I'll collect terms first. I'll move this negative 3x over here by adding it to both sides. Adding 3x to both sides gives me 5x equals 10. Divide both sides by 5, and I get x equals 2. Simple enough once I get the equation set up. And that's problem number 3. All right, let's keep going. All right, problem number 4 on your test will be referenced in section 4. Section 4 dealt with special parallelograms. What made them special is that they just had extra qualities, extra theorems, extra properties attached to them. The properties attached to these figures, they were very familiar figures to us, namely like rectangles and squares. But the one that will be referenced in your section 4 notes will be the shape of a rhombus. So we're going to be given a rhombus for problem number 4 tomorrow. Now, what is a rhombus? A rhombus is a parallelogram. And the fact that it's a parallelogram forces it to have all that other baggage that we just referenced in section 2 and section 3. Diagonals will bisect one another. Opposite sides will be congruent. Opposite interior angles will be congruent, so on and so forth. Okay. But because it's a rhombus specifically, it will have a couple extra things. And so we'll talk about those here. Draw a rhombus first. Close enough. All right. And then I'll be drawing diagonals like so. Okay. So this is a rhombus. So again, just to break down what a rhombus is, it's going to be a parallelogram, meaning these two sides are parallel and these two sides are parallel. And what makes a rhombus is that it's a parallelogram who has 4 congruent sides. A square, for the record, is a specific type of rhombus. This will obviously not be a square. And then we'll be given some information. This will be pulled directly from our notes. So this little sliver down here is 61 degrees. And then you're going to be given a couple of numbered angles you're going to be asked to solve for, like so. And your job will be to solve for each of the missing angles. So it'll give you something like this. Measurement of angle 1 equals blop. Measurement of angle 2 equals blop. Measurement of angle 3, so on and so forth. However many numbered angles there may be. Now, most of these are going to be very, very fast solutions. Just direct references to different properties. Namely, these first 3 are going to be very fast. Little to no work needed. Angle number 4 here is going to be a little trickier. Okay, angle 4 is going to be a little trickier. I'll talk about that last. But let's reference these one by one. So first off, angle 1 right here in the middle, we're actually going to be referencing a property that is unique to the shape of a rhombus. Not unique to rhombus in that like it doesn't happen for any other shapes. It's just that if I tell you it's a rhombus, this will always be true. Namely, the diagonals of a rhombus not only bisect one another because it is a parallelogram still, but they have to intersect at a right angle, forcing all 4 of these little diagonal intersection angles right here to be right angles, meaning angle number 1 here is 90 degrees. Angle 1, check. All right, let me put a box around all these guys. All right, angle 2 and angle 3 are actually going to end up being congruent or equal to each other. These 2 guys will have to match because of a different property with a rhombus. Not only do these diagonals have to bisect one another, chop each other in half, not only do they have to intersect at a right angle, forcing angle 1 to be 90 degrees here, but also these diagonals bisect opposing angles. In other words, this top left corner, the whole corner up here needs to be the same as down here, right? Because it's a parallelogram, but this diagonal has to chop it in half. So whatever measurement this whole top left corner is, 3 and 2, angles 2 and 3 right here, need to be the same as the other because this diagonal will chop it in half. Okay, well, that doesn't tell me the exact measurement yet, but because I know that this is 61 degrees here, and this same diagonal still has to bisect at this bottom right corner, that forces this angle here to, in turn, be 61 degrees. Now, I didn't need this guy, but this is just to kind of show you that these 2 are 61 degrees. That's going to force these 2 each to be 61 degrees. Because 61 plus 61, that's 122 degrees down here. That 122, because it's a parallelogram, forces this one to be 122. And again, because the same diagonal bisects it in half, that 122 divided by 2 gives me 61 and 61. So these 2, again, little to no work needed. Just kind of copy and paste that guy for each of those. So the tricky one here is the measurement of angle 4, this guy right here. Because I'm not told any information about this top right corner. I'm not really told anything about this bottom left corner, but I need to find this little sliver. I'm going to be referencing a couple things here. One of which being that this diagonal needs to bisect whatever this corner is going to be. So let me scroll down here. I'll come back to what measurement of angle 4 equals in just a second, but let's get a little room here to break this down. So first things first, let me draw like a little cleaner version of this same rhombus. Okay, I want to get rid of the diagonals just so I can clean this up a little bit. Okay. All right, so what we already know is that this bottom right-hand corner is 61 and 61. So if I just add those together, that tells me what this bottom right corner is here. So in this case, it's 61 plus 61, or 122 degrees. Okay, that's that whole corner. And because it's a parallelogram, or I could add up angle 2 and 3 that I just solved here, it's also 122 degrees up there. Now, the piece that I don't know about are these guys. So these are unknowns. So for instance, if I want to know this bottom left angle, let's just call that, say, I don't know, X, because it's something I don't know. But because opposite angles are congruent in a parallelogram, that means that whatever this bottom left corner is, the top right corner must also be the same. These 2 need to match. This will be useful because this is still a 4-sided figure fundamentally. And a 4-sided figure, the internal angles need to add up to 360 degrees. So if I add these together, I get x plus 122 plus 122 equals 360 degrees. All right, some of you might have done this. You might have said like, all right, well, if these are both 122, if I add those together, that's 244. If I subtract that from 360, that tells me what's left over for these 2, divide that by 2, and I get a single corner. Algebraically, I'm going to show that right now. So if I collect like terms, x plus x gives me 2x. 122 plus 122 gives me 244. And it's still equal to 360 degrees. Okay, so if I subtract 244 from 360, don't be a hero, use a calculator. 360 minus 244, 116. All right. So if I subtract 244 from each side, 116 degrees is going to equal 2x. Basically, that 116 degrees is what's left over to split between these two angles. And because they have to be congruent or the same, I can just divide it by 2. That tells me that that x is going to equal that divided by 2, or 58 degrees. Okay. So x here has to be 58 degrees. Well, I'm not done yet, because angle 4, you'll notice, is that little sliver right there. All right. It's not the whole corner. But again, I'll reference the fact that these diagonals have to bisect that whole corner. In other words, it's going to cut that in half. So measurement of angle 4 is simply going to be 58 degrees, or whatever value I got in this case, that 58 degrees divided by 2, in this case, 29 degrees. So that 29 degrees will be my angle 4, that missing little sliver. All right, so like I said before, angle 4 here was the high maintenance one to solve for, but the other 3 were pretty much automatic. All right, so that's problem number 4. Again, you will see a rhombus specifically on your test tomorrow. Let's keep going. Problems 5 and 6 will both be referenced in section 5. Section 5, if you recall, took a step back from parallelograms to talk about 2 other specific types of quadrilaterals, namely trapezoids and kites. The first one I'm going to reference is the first one, trapezoid. So as I draw this figure, let me just remind you what a trapezoid is. A trapezoid is a 4-sided quadrilateral with exactly 1 pair of parallel sides. Meaning that the other 2 sides, or the legs, are not parallel. So you'll be given something like this. Okay, there's a pair of parallel sides, and I'll label the corners as follows. All right, so that's a trapezoid. 1 pair of parallel sides, the other 2 sides are not parallel. If I were to extend these off, they'd run into each other somewhere. Okay, so one of the properties we learned about trapezoids was something called the Mid-Segment Theorem. Mid-Segment Theorem did this. Each of these legs, the non-parallel sides, has a midpoint. Call it M and N. And if I connect those 2 midpoints, I create what's called a midsegment. Now, this midsegment has a couple of properties. First off, one that I will not be using here is that this midsegment is also parallel to the 2 parallel bases. So however many midsegments I create, they're all parallel to each other. Create this series of parallel lines. That's not what I'm going to be using here. For this problem, I'm going to be using it for the second property, and it's going to be referencing this. Let's say A to B here up top is 9 miles. And from D to C here is 15 miles. I can use the second property about midsegments to figure out the length of the midsegment. Essentially, what I'm going to be doing is I'm going to be taking the average of the 2 base lengths to figure out what the missing midsegment length is. So on this problem, you're going to be given a trapezoid like you see here on your screen, and you're going to be asked to find the length of the midsegment. In this case, find the length of MN. It may use different letters on tomorrow, but essentially find the length of the midsegment. The formula that we learned here is that this length is basically the average of the 2 bases. Now, if I take the average of anything, I add that number of things up and then divide by the number of things that I added. In this case, I'll simply be adding the 9 miles plus the 15 miles, the 2 base lengths, and then dividing by the number of things I added. I only added 2 things, so I divide by 2. So this, again, finds an average. It will tell you what's exactly in between 9 and 15. So pretty simple math here. 9 plus 15 is 24. Feel free to use a calculator. All right. 24 divided by 2 gives me 12, meaning that the length of this midsegment is 12 miles. Quick and simple. Expect different numbers, obviously, on your test tomorrow, but you'll find the length of a midsegment by finding the average of the 2 base lengths that you are given, however big or small. All right, that's problem number 5. Last problem, also from section 5. And the other namesake to this section was this other quadrilateral shape, namely a kite. So you're going to be given a kite. Just to remind you what a kite is, a kite, by definition, has 2 pairs of consecutive, or in a row next to each other, congruent sides. So here is a kite. In other words, these 2 sides are congruent to each other. These 2 sides are congruent to each other, but they're not congruent to the other pair. In other words, whatever length this is, it's not going to match this guy, for instance. Okay. And then you'll be given labels like this. All right. So again, the signature look of a kite, you have this kind of wedge shape here. For those familiar with sea creatures, this is similar to like the shape of a manta ray. And so one of the properties we learned is that these wings or arms of the manta ray, these 2 angles have to be congruent to each other. That's one of the properties that we learned about kites. But you'll be given the following information, right? This is pulled directly from our notes, so it'll be similar to what you were given on your test. You'll be given 2 of the angles. Angle E is 115, angle G is 73. And you're going to be asked to find one of the missing angles. In this case, in this problem on our notes, we had to find angle D. So in this case, find the measurement of angle D. All right, so for this problem, we're going to be referencing the shape of a kite. Namely, that in this kite, these 2 angles, the arms or the wings of the kite shape, have to match each other. So my job here is to find D, and we'll call that our unknown, say X. And because these 2 are congruent, that means that whatever I find out here has to match whatever I find out here. In other words, I could call this X as well. And so what I'm essentially doing is something that we've done a couple times throughout this cheat sheet. And I'm basically going to be adding up each of these angles. And because it's still a 4-sided quadrilateral, these 4 angles need to add up to make 360 degrees. It's unique to a 4-sided figure. So I can just simply do that algebra. In other words, I could have X plus 115 plus 73 equals 360 degrees. Again, unique to a 4-sided figure. Had it been like a 9-sided figure, it'd be a different number here. But the namesake for most of this unit is quadrilateral. So in this problem, that's what I'm going to be looking at. All right, just like before, I combine like terms. So X plus X gives me 2X. 115 plus 73 gives me 188 degrees. And this is still equal to 360 degrees, right? I've combined like terms. Now I just move stuff away using inverse operations. So if I subtract 188 from both sides, 360 minus 188 gives me 172. 172 degrees is equal to 2x. Another way to think about it, after the 115 and 73 are taken out of the 360, there's 172 degrees to split between these 2 guys. Since they have to be the same, I just divide by 2 to find out what the single is. So when I divide both sides by 2, 172 divided by 2 gives me 86 degrees. Done. Thus concludes our Chapter 7 cheat sheet. I'll go ahead and stop recording right there.